the slideshow set up and go from the current slide. Forgot to do this. All right. And I'll even turn on the projector for you today. I feel magnanimous. Okay. Now, like I was saying too, I have a ton and a half of announcements to do today, so I'll try to get through them quickly. But some of these are pretty important. There's 2 scholarship opportunities, so I wanted you to hear from both of these. One's at UAB and one is at UA, okay, Tuscaloosa. The scholarship opportunity, the one at UAB is available for those who are completing all requirements and graduating this term, okay? So if you're still going to have a course to do for summer, you may not qualify for this one. Or if you're going to be back here in the fall, yeah, you definitely don't. But if you are graduating this term, okay, UAB Presidential Scholarship covers the cost of tuition for 4 semesters, that's for 2 years, okay, provided the student maintains a 3.0 GPA at UAB. Okay, the student must apply and be admitted to UAB by March the 1st. That's next Thursday, I think it is. So I don't know if this gives you enough time to do it, but I wanted you to hear this, okay? And if you know of anyone else that may qualify, they need to get moving on it right now. Have an earned associate degree at the end of spring semester. That's why I said you must be graduating this time before fall semester in which they can enroll. Official transcript must be provided indicating graduation date. 3.5 minimum GPA here. Non-transferable coursework will not be calculated in the GPA. Not have any 4-year institutional credit. Exception courses taken while in high school, that would be okay. Not be a former degree-seeking student at UAB. In other words, you couldn't have gone there, come here, and go back there. You don't qualify. Must be an Alabama resident, okay? Must be willing to assist with transfer, recruitment, events, and efforts as a transfer representative for UAB. Examples, tours, community college visits, transfer day at UAB. If you meet the criteria and are interested in attending UAB, please submit the official, blah, 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 your transcript, all that kind of stuff. I have the information. And guess what? This went to you. If you checked your email, you should have gotten this, okay? So check your Lawson State email and you should see it. And tell anyone else you know that may be graduating this term. And you also got the one from Tuscaloosa. I'll try to do it quickly. This is even worse. All information due by Monday, the 26th, okay? So, scholarship opportunity is available for those who are completing all requirements and graduating this spring, just like before. University of Alabama Presidential Scholarship covers the cost of tuition for 4 semesters, just like the one at UAB, provided the student maintains a 3.0 grade point average, just like UAB. To receive the scholarship, the student must have earned an associate's degree and maintained at least a 3.5 cumulative GPA here. The student must be admitted and have submitted scholarship application to UA by March 1st. But all the stuff has to be in by Monday. You may not have been accepted yet, but that still is going to fill it. Student cannot be a former degree-seeking university at UA. In other words, you couldn't have gone there, come here, and go back there, or any other 4-year institution. And the value of the presidential scholarship will adjust the cost of tuition increases, currently valued at $50,000. Okay, so it's not chicken feed. Okay, if you meet the criteria, blah blah blah, and that deadline is Friday, 5 p.m. Friday, February the 26th. Oh, both of them are. Okay, you have to have all your stuff in. You don't have to be accepted, but all the stuff has to be in. I didn't read this last part because I thought it was just blah blah at the bottom, but let me see. If you meet the criteria and are interested in attending UAB or UA, okay, these are almost identical, please submit an unofficial copy of your transcript, resume of activities and or work, as well as biographical letter of interest detailing your educational goals and why you are the best person to receive this particular scholarship no later than 5 p.m. Monday, February 26th. Okay, and both of these go to Mr. Dorian Wailun, who is here at, he's on both campuses. He's down in Superior Services, and I can head you that way. So both of these things have to be in to him by Monday, but you don't have to be accepted, and you have to be accepted by March 1st, which is Thursday of next week. So if you want to see these, you can certainly look at them. Check your emails; they're both out there. And why we got them so late? They were sent yesterday morning, early. Yeah, 6 something yesterday morning. All right, graduation meetings. Are any of you graduating this term?
Well, I'll be graduating over the summer.
What's that?
I'll graduate over the summer.
Okay. Are you going to walk this spring?
Do I have to walk?
You don't have to march. No.
I don't want to march.
Don't. Okay. I was going to say, if you're going to be walking with them, you probably need to go to these meetings. But if not, you can wait this summer. Okay. All right. But none of you are? Okay. Well, then none of you need to hear that last announcement, did you? I should have asked that question first. Okay. And Mr. Rossi is still trying to find math team members. She has a few of you. I hope some of you are participating. This Thursday, tomorrow, we have a meeting 2 to 3:45 in the afternoon. So I'll probably be out of the office during that time. Okay? Yeah. Okay. Now, tutoring. I'm guessing that most of you probably don't need tutoring, but you might be great tutors. I'm guessing you would be. And this is just to emphasize the need. On the Bessemer campus, the tutoring schedule for the Space Center, which is downstairs on the first floor, they only have tutors there Monday and Tuesday. Okay? So if you can tutor, especially Wednesday, Thursday, or Friday, they may really be interested in hearing from you. Now, we also have tutoring up here in Student Support Services, and that's any day of the week, but they may still be needing tutors. So if you are interested, Miss Hollins is the person up here in room 202, and downstairs, I think it's 105 or something like 103 or 105, something like that. That would be, I don't know. I know Dr. Davis coordinates it, but there is a guy down there who would probably be able to help you with that.
You know what they pay?
They pay pretty well. It's at least minimum wage. I think maybe even a little above, but it's limited hours, whatever you tutor. But it is not bad pay. The pay is pretty good. For part-time work. Okay. Look at the tutoring on the Space Center on the Birmingham campus. Monday, Tuesday, Wednesday, Thursday, Friday. Okay. We're Monday, Tuesday. Okay. And they have a lot more people tutoring as well. So let somebody know if you're interested. And they do pay. Now, I can throw this one away. This is homecoming week. And today being Wednesday, at 12 o'clock noon in our cafeteria down here in this building, they're having Name That Tune. Okay? So if you want to go participate, it should be a lot of fun. If you're over on the Birmingham campus at noon, though, they're having More Than History. The speaker is Mr. Eric Guster, and that's at the ACAT Auditorium on the Birmingham West Campus. Tomorrow, Thursday, here on this campus, on both campuses, at 11 o'clock in the morning, they're having a cookout. Now, as long as it's not raining, it'll be outside, just outside in the courtyard there coming in is where they usually have it. Somewhere there, front of the front of the building that's in the rear of the building. Okay, the one that faces the interstate. Back there, that entrance there, it'll either be the lower level or upper level. That's usually where they have it. On the Birmingham campus, I think that's near the Student Center, Leon Kennedy Student Center. Then there's the Cougar Choice Awards at 5:30 in the evening, and that's in the A.G. Gaston Auditorium on the Birmingham East Campus. Okay, Friday, day after tomorrow, back to the 90s, Party with a Purpose, shelter items, blanket, non-perishable items, toiletry items. That's from 7 to 9 in the evening at the Leon Kennedy Center on the Birmingham West Campus. So bring an item, get in for free. Okay, Party with a Purpose. And you can dress up like people from the 90s, and they have some of the TV shows and things like that if you're really interested in that. And then the homecoming game, they had one last Monday that they were celebrating too, but this will be the actual homecoming game with a homecoming parade and prep rally starting at 4 in the afternoon from the gazebo to the gym on the Birmingham West Campus. And then in the evening, both teams are playing. The women play Gadsden State at 5:30, and the men play, I think, at 7:30. That's Arthur Shore's building, the gymnasium, also called Arthur Shore's Fine Arts Building. Fine arts and gym go together really well, don't you think? Yeah. Okay. But anyway, that's at the Birmingham West Campus. Okay. And I bet you got all this information too. So that's over with, I think. And I have a meeting with the dean from 2 to 5 next Thursday. Okay, not this Thursday, but next Thursday. That's March the 1st. So there's a meeting over in the ACAP building. It's all department chairs and that kind of stuff. So, no new students came in. That's one reason to give all the announcements, but I'll put it on YouTube. Okay, any questions on anything else? Had a few questions before class. Do any now? Okay, then let's move on. 2.3, Chapter 2 is still differentiation, and 2.3 is product and quotient rules and higher order derivatives. So if you thought derivatives were all as simple as they were in 2.2, guess what? They can get a little more complicated. Okay, the objectives here, we'll first find the derivative of a function using the product rule, find the derivative of a function using the quotient rule, find the derivative of trigonometric functions, and find the higher order derivative of functions. Now you might say, didn't we already do 2 trigonometric functions, right? What were they? Sine and cosine. But see, there's 4 more trig functions. You can't do those until we know, especially the quotient rule. So that's why the other 4 are going to come after we do the quotient rule. And the next is find the higher order derivatives of functions. Second derivatives, third derivatives, 15th derivative, whatever. Okay. So let's start with the product rule. You've learned that the derivative of the sum of 2 functions is simply the sum of the derivatives, right? The derivative of the difference of 2 functions is the difference of the derivatives, right? The rules for the derivative of the product, do you think that would be the product of the derivatives? No. In fact, one of the guys who developed calculus, name was Leibniz, the German guy, okay, not Sir Isaac Newton. And when he first published it, he thought the derivative of a product was the product of the derivatives. And he found out he was totally wrong. Okay? Products and quotients don't follow the simple rules like sums and differences. Okay? They're not quite as simple. So here's the product rule. The product of 2 differentiable, I don't know why that line's in there. It's just a line. Okay? F and G. Now, number 1, a product of 2 differential functions is differentiable. It's just not the product of their derivatives. Okay? Moreover, the derivative of F times G, if both of those are differentiable, and by the way, when we say differentiable, that has to be over the same domains. If F is here and G is there, then the differentiability has to be over the similar part of the domains. Okay? The derivative of Fg is the first function times the derivative of the second plus the second derivative function times the derivative of the first. Okay? So in other words, d by dx, I like saying that, don't you? Of the product f times g is f dg plus g df. Okay? So remember that. It's not just the product of the derivatives. That doesn't work. It's the first times derivative of the second plus the second times derivative of the first. And always a plus for the product rule. Okay? Now, the product rule can be extended to cover products involving more than two factors. For example, if you have a product of three, like f and g and h are differentiable functions of x. Now, they all have to be differentiable in their own right over the same parts of the domains. Okay? So as long as that fits and works, then the product of derivative of a product of three would be derivative of the first times the product of the other two, plus the derivative of the first and the third times the derivative of the second, plus the first times the second times the derivative of the third. Okay? So you just extend that. Okay? So, how do we do this? Derivative of y is equal to x sine x cosine x. What would that be? And the order doesn't matter. Say again? 2x times. Okay, no, okay. Yeah, it is cosine and sine, but it's this function times that function. And that is cosine sine. But don't do the derivative of this times the derivative of that. Don't do that. It's the derivative of this times these two plus, plus x squared. Okay, what do you say? Cosine times derivative of sine is cosine times cosine. So that's cosine squared. So it's x squared. The second term is x squared plus cosine squared. And they wrote it cosine times cosine. Okay, that's fine. Next. This one times the derivative of this one. What's the derivative of cosine?
X squared sine x.
What's the derivative of cosine? Negative sine. So that would be, okay, they wrote it x squared sine x, negative sine x. So I would have written that as minus x squared sine squared x, which they ultimately do here, which gets us down to 2x sine x cosine x plus x squared cosine x, and they factored out the x squared minus sine squared x. Now, for those who remember their tricks so well, I know 3 of you, 4 of you probably do, don't you? Okay? That looks a lot like cosine 2x, doesn't it? Yeah, the double angle formula for cosine. Okay, but we're not going there now. But just to let you know, there's several ways that you can write these solutions. Okay, so now this is the first book that I've ever taught from that jumped right into products of 3 functions. So I found it interesting they did that and gave you that rule this early. Usually they just start with product of 2. This one dropped right in the product of 3 before they even give you an example of a product of 2. In fact, you did the product of 2 there. Okay. So the derivative of a product of 2 functions is not, in general, given by the products of the derivatives of the 2 functions. That's what Leibniz thought it was until he checked it, found out he was totally wrong. Okay. So here is your example 1, and it says, find the derivative of h of x when h of x is the product of 3x minus 2x squared times 5 plus 4x. Now, time out. There are more than one ways to do this problem. What would be one way? If we hadn't given you the product rule, what could you do? Second?
Take the derivative of each.
Okay, yeah, if we hadn't given you the product rule, you could multiply those two together. That's a binomial. And just do your binomial rule. I mean, a polynomial rule, right? So you could certainly do that. We'll come back and do it, okay? I promise we will. But let's use the product rule first. And what does the product rule tell you? Can I just call it H prime? Because it's easier to write than D by D. Though D by D is funnier, it's more fun to say. Okay, H prime of X would then be what? Okay, you're going to do the first one. 3x minus 2x squared times 4. Perfect for the first part. Plus, you said, right? I'm sure I heard a plus, didn't I? Yes. Okay, times 5 plus 4x. 3 minus 4, I can't write, x. You got it. Okay? Let me clean that up a little bit. I don't want you saying, oh, that's what you said it was in class, this squirgle here. Okay. So we still got work to do, don't we? What is the product of those that first product going to turn out to be? Help me, help me. 12x minus 8x squared. Now we got to FOIL, don't we? Plus, okay, you can do that. Let's go on and do the 15 first, okay? That's the first. And the outers are minus 20x, and the innards are plus 12x, and the last are, second, say that one more time, minus 16, what else you say? X squared. Okay, good, I couldn't hear, okay. So let's see if we can combine some like terms here. And what like terms do you see? Looks like to me 15 doesn't have one, so I'm going to write down 15. That's the constant term. And then when we go to our linear terms, you have a plus 24 minus 20, which would be, and this is x. Help me, help me. Plus 4x, okay? And then you have two quadratic terms, and that is minus 24x squared. All right, that's what we say the product, the derivative of the product of those two polynomials are. So let's do it the other way, just to see. Let's start off by doing our foiling up here. H of x is equal to, first terms, 15x. Outers would be plus 12x squared, right? Okay. Innards would be, a little louder, minus 10x squared, is that what I heard? Okay, and lastly would be the last, and that would be minus 8x cubed, right? Okay, now let's combine like terms. Sorry, started to get ahead of myself. I don't like to do that. I'd rather be behind myself. Okay, let's combine like terms, and that becomes 15x plus 2x squared minus 8x cubed. Okay, that's your h of x, if I did it right. So now let's do h prime. And what would that be? 15 plus 4x ding, 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 ding. Yes, we have a winner. Okay? It's the same both ways. And frankly, in this one, it's about 50-50. I'd say it's actually probably easier to go and multiply them together first and then take the derivative. Okay? Because there you had to take the derivatives, two sets of derivatives, and then multiply polynomials anyway, and then combine like terms. So I think this was actually a little easier. A lot of times it's not. Like when you have x squareds and cosines and sines, yeah, there's no way to simplify that any. So you use the product rule. Okay? And they did the same thing. They just rearranged the order on both of theirs. All right. That's how we did it. Let's see how they did it. Can I leave that? I mean, do I need to leave it a little longer, or y'all got it? Okay. So let's see what they do first. H prime of x would be the first, which is 3x minus 2x squared times the root of the second, which you did in your head, plus the second, which is 5 plus 4x times the derivative of the first, which is 3x minus 2x squared. Okay, the first term then brings down to be 3 minus 2x squared, and derivative of the second, which you did already, was plus times 4. Okay, plus bring down the second, and then take the derivative of the first, which you did 3 minus 4x. Okay. And then we have to multiply our polynomials. The first is the binomial times the monomial, which is simply 12x minus 8x squared. The second is a product of two binomials, which you FOIL or whatever you want to do with it, and that gave us 15 minus 8x minus 16x squared. And then you combine like terms with those, and you get minus 20, and they rearrange the order, minus 24x squared plus 4x plus 15. And that's your derivative. And then they skip the other way to do it, and they also skip example 2, they skip example 3. Okay. Just realized I said something wrong to the dean. I said this book gave, it's just certain of the exercises they show at larsoncalculus.com. So let's us do then example 2. Okay? Find the derivative of course this will be a little more involved one. Y is equal to 3x squared sine x. What does that represent? 3x squared sine x? A product of two different functions. 3x squared times sine x. Okay? So, what might we use? Product rule sounds like a capital idea. Y prime, which they don't usually use y prime, but it sure is easier to write than d by dx, but it's more fun to say d by dx. Okay, what will y prime be? 3x squared. I know it was a long time since Monday. Yeah, it's cosine. Okay. Now again, what I do, I picture that sine curve. Okay, and at 0, its slope is 1, and at pi halves, its slope is 0. That's exactly what the cosine value is at 0, and the cosine value is at pi halves. So that's just cosine x. Okay? Next.
Plus 6x
6x
times sin x.
times sine x. You got it. That's it. So you didn't need parentheses there, but I'll just take them off then. 3x squared cosine x plus 6x sine x. Now, this is where I really get into problems with WebAssign. I don't know if that's how they're going to give their solution, but this is also a perfectly correct solution. Factor out a 3x, and that leaves you x cosine x plus 2 sine x. That's no better solution than the other one. Perfectly fine. No reason to do that, but it's a correct solution. Okay? Now, what do they give in the book? They actually do the second step. So I bet you that's what they would have done at WebAssign. And they would have said, if you wrote down that as your answer, it said, wrong, and it's not wrong. It's correct. It's absolutely a correct answer. Okay? That's why I really don't care for WebAssign. They tell you you got it wrong when you actually had it right. Okay? How about, that was so much fun. Don't want to do another? Yes, okay. All right, let's erase that one. And let's do example 3. Find derivative of y is equal to 2x cosine x minus 2 sine x. Okay? Y prime then would be what? Did I hear a 2x being whispered? Times a negative sine x. I put the negative in front. Okay? That's the first part of the first term. Say again? Okay, are you doing the second one here? Let's not forget the second part of your product rule.
Oh, plus.
Okay, yeah, you're going to have a plus there.
So then we have.
It would help to do that. Okay. Okay. 2 cosine x. Okay. Now let's do the second one term. What is its derivative? It's what? Minus 2 cosine x. Because you see, that's just a coefficient. It's not, you might say it's a product, but the derivative of that is 0. So don't mess with that. Just do the coefficient minus 2 times the derivative of what's left. Derivative of sine is cosine. Okay? Now what you notice happens now. They were, those add to 0. Okay? So your answer is just that. Negative 2x sine x. Yep, they got it right. Good for them. Okay. Now, if you had noticed, you could have factored out the 2's to begin with and just had x cosine x minus sine x, and then the 2 just stays out here and take the derivative of those. That would have made it maybe just a little bit easier, because it's real easy to forget about the 2's, but you know, the way you did it was perfectly fine. I was just doing how you said. All right. Any questions on that? All right. The product rule, even though it's a little bit different, A little more complicated, but still pretty straightforward, right? Okay. Now comes the quotient rule. And its level of complexity increases significantly. Do I need to keep this up a little longer, or are you okay? Huh? Okay. All right, now we'll do the quotient rule. All those tricky little quotients. Never liked dividing, did you? Never mind, I didn't say that. Here's the quotient rule. The quotient of 2, now both f and g have to be differentiable functions. If they're not, don't even try to take a quotient of them. Just like adding or subtracting or multiplying. You can't do them if they're not differentiable. Don't try to do, just making them a quotient is not going to make them differentiable. So if they're both differentiable, then the quotient of them is also differentiable for all values. Remember, one thing we have to do, remember now that g is in the denominator, okay? And remember, we always said that about the domains. If its domain was here, g's domain was there, then you're limited to the domain that's common to both. But not just that, you also now have to exclude from that domain any values from x which make g of x equal 0. Because you can't divide by 0 either, okay? So you have that complication. But that's minor compared to what the rule is, okay? Moreover, the derivative of f divided by g is given by, now get this one, the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the square of the denominator. Okay? Boy, a mouthful and a half, isn't it? Okay? You want, I can't remember if this is my Indian student that I tutored, or I just think of it because he said it. But here is a little bit, to me, easier way to remember. I mean, I remember it that way because that's how I learned it. Okay? But then later I've learned this. Low d high minus high d low over low low. Denominator. Okay? That just sounds better than trying to remember, well, first, where do you begin? It's the denominator times the root of the numerator minus the numerator times the root of the denominator over the denominator squared. Yeah, that's the rule. But it's a little bit easier as low d high minus high d low over low low. Do you agree? To me, it's just more fun anyway. I don't know if it's easier. But remember, the g of x should never be 0. That's that part.
Catchier anyway.
What's that?
I was just saying it's catchier anyway.
Yeah, it sure is catchier. Okay. Yeah. Low d high. Just remember to start low and go high. Okay. Low d high minus high d low over low low. Okay. Good deal. Books don't give you that kind of stuff most of the time. Shame on them. Okay. I don't think they do anyway. I haven't looked at this one to see if they do. All right, so let's do example 4. Oh, they have a proof there. I'm sure y'all wanted to do the proof in class, right? I'll let y'all do that at home, okay? Okay. Let's move on to example 4. Are any of you, I think I asked this before, pure math majors or all of you pre-engineering? Oh, you kind of are? Okay. You probably want to do that proof then, right? Oh, boy. If you need help with any of those, I'll be glad to try to help. Okay. You can see it's sort of long and involved, but it works. All right, so let's do example 4. Find the derivative of y is equal to 5x minus 2 over x squared plus 1. So what would be your y prime? You tell me. Why is my pen not writing? There it is. Now it's a y double prime. We only need a single prime. How do you begin?
X squared plus 1.
Okay, low, which is x squared plus 1. Times 5. D high. Minus 5x minus 2. Okay. That's high times 2x. That's D low. Over
x squared minus 1 squared.
plus 1. That's my job to write it wrong. You're to get it right, okay? All right. All right, that's it. Now, we can simplify this sum, and let's do so. What would that give you in the numerator? 5x squared plus 5 minus 10x squared. Okay, that would be a plus then, wouldn't it? Minus times plus. See, you got this minus times that, yeah. So that'd be plus 4x, right? All right. And that's all over. You know, I'm perfectly happy leaving that as a square. X squared plus 1 squared. There's no reason to multiply that out, I don't think, okay? So what does that give us in the numerator? Help me.
That'd be 5 minus 5x squared plus 4x.
Okay, did you say a minus 5x squared? I thought so. What you said. Okay. Plus 4x. Plus 5. Right.
Oh, I'm sorry. I thought I said that first.
Oh, I'm sorry. Okay. You may have said it. I thought you were saying the 5 for the 5x. Okay. My hearing's not good. Over x squared plus 1 squared. There's no reason to multiply that one out because you see this doesn't have any factorization beyond x squared plus x squared. This one, you could try factoring it if you want to, but I don't think that x squared plus 1 is going to be a factor. So why mess with it? So that is your answer. Always try to factor out if you can, but if you see there's no possible common factors, why take the time? So let's see if we did it right, since this isn't shown. Oh, no, it is shown here, okay? But sure enough, it is. I knew they were probably going to put it in descending orders of power. That's why I was listening for that, so that's why I didn't hear what you said. Okay.
Does it have to be written? I mean, should it be
You don't, no. Any order will be fine. That's why I say, when I'm grading your test or things like this, if I see it's the correct answer, you're going to get credit for it. If I were doing that on testing you through WebAssign, then they may or may not recognize the correct answer, and then I have to go back and retest it. So why do all the extra work? You know. So anyway, I just go this route. Any questions on that before I erase it? We'll see how they did it. Any? If not, let me erase this, and let's see what they do. They do d by dx, they like that, don't they, of 5x minus 2 over x squared plus 1 would be the denominator, x squared plus 1 times the derivative of the numerator, which is d by dx of 5x minus 2, minus the numerator, 5x minus 2, times the derivative of the denominator, which is d by dx of x squared plus 1, all over x squared plus 1 squared. That's the quotient rule. Or low d high minus high d low over low low. Okay. And that would then be derivative of 5x minus 2 would just be a 5. Now why they put that in brackets rather than parentheses, I'm not sure, but they did. And here's Chaston. Okay. Are you graduating this term? Okay. Did you check your emails about there's some scholarship opportunities at UAB and UA? You saw that. Okay, fantastic. All right. We're doing the quotient rule, which is a lot more involved than just the regular derivatives. And we'd already done the product rule, which is somewhat more involved than the regular derivatives. So you have to listen to catch up. But what you have is the denominator for the quotient rule. The denominator times the derivative of the numerator, which would be, for this problem here, derivative of 5x minus 2 over x squared plus 1. The denominator, x squared plus 1 times the derivative of the numerator, 5, minus the numerator, 5x plus 2, minus 2, you got me saying it now, times the derivative of the denominator, which was 2x, okay? All over the denominator squared, x squared plus 1 squared. Which then the next step will be distribute across the parentheses, which would give, whoa, I hit the wrong key. 5x squared plus 5 minus 10x squared. Aha! Now notice what they did. They kept the minus outside and just multiplied those two together and did the minus times 10x minus 4x, 10x squared minus 4x. But kept the parentheses there, which gave them another step, but then they didn't do the sign error. So if that helps, do it. Okay. That would be minus 5x squared. And then they didn't show how they combined like terms or cleared the parentheses or changed the signs or anything. They just did it. Plus 4x. Okay. 5x squared minus 10x squared is minus 5x squared. Minus times a minus 4x is plus 4x. And then a plus 5 over x squared plus 1 squared. And there's no way you can reduce that. So there's no reason to try to factor. You can try, but you know if it won't work, go back to a simpler form. Any questions on that? Okay. Now that was example 4. They are skipping examples 5 and 6. So let's go back and do examples 5 and 6. Okay. Find an equation of the tangent line to the graph of f of x is equal to 3 minus 1 over x over x plus 5. At the point 1, negative 1. No, set it backwards. Negative 1, 1. Okay? Now, as Jeremy and I illustrated earlier, I'm a cynic because I always want to make sure that what they're telling me to do is doable. In other words, if it says find the slope of the tangent line of this function at that point, I want to make sure that point is on that function. Okay? So what I do here is plug in a minus 1 for your x and see what the y turns out to be. So 3 minus a 1 over minus 1 would be, yes, that becomes a plus 1, so 3 plus 1 is 4 over minus 1 plus 5 is 4. 4 over 4 is 1. Yes, that point is on the line. So we will proceed. Okay? I always do that because I just don't trust them. You know, they're out to get me, you know, so I always check it. All right. So how are we going to do that? It says find the equation of a tangent line. Does someone want to remind me what the equation of a tangent line is going to look like? Y is equal to mx plus b is a perfectly good thing to do. Okay? But what's the m? Oh, that's the slope. Okay, yeah, got it. How do we find the slope? Take a derivative, y'all remember the magic question. Okay, so we're going to take the derivative just to find the m. And then we're going to have to figure out a way to find the b. But I think we'll be able to figure out one to do it. Don't you? Don't you have confidence we'll be able to do that? Okay, good deal. All right, so to get the m, we find the derivative of f prime of x. And what would it be? Now, a little bit of a timeout here. Let's jump this over here. I want to rewrite that function. I don't like having variables in denominators if I can avoid them. I don't like having variables under square roots if I can avoid them, radical signs. So how would you rewrite that one? 3 minus you got it. Okay. Over x plus 5. I far prefer it written in exponential notation rather than rational notation. If you can, I find that easier to take derivative. Now let's take derivative of that one. Now I don't know if you remember back when you did this in algebra, and they would tell you, hey, write this in a certain form. That's why they had you doing those exercises. You probably thought at the time, they're just messing with me, just giving me something else to do, but there was a reason for it. Okay, so now let's do f prime. What would that be? Yep, there's your good old low. Chester, you weren't in here for me to give you the sort of lyrical version of how you do the quotient rule. Were you? Did you hear it? Low D high minus high D low over low low. Low meaning the denominator times the derivative of the numerator minus the numerator high D low times the derivative of the denominator over low low the denominator squared. That big long hairy verbal thing, but that sounds, I don't know what it sounds. Okay, so we did the low, and what do we do next? Okay, x to the negative 2. Now, I'm sure you meant to do this, that minus 1 times minus 1 is plus, and that's why it's not a negative there anymore, and then drop that by 1. So yeah, there's D high. Next, minus times 1. Ooh, I can live with that. Okay, over x plus 5 squared. Okay, so this will be, now that's a fairly strange thing to distribute, but it's doable. X times x to the minus 2. What would that be? Say again? Not x, x to the minus 1. You add exponents when you're multiplying. Same base, different exponents. Keep the base, add the exponents. Okay? Next. Plus 5x to the minus 2. Right? Next. Minus 3. Say that one more time. Plus x. They sneak up and grab you, don't they? Okay, you got to watch for them. X to the minus 1. Over. X plus 5 squared. Okay, now what should we do? Second? Combine like terms, and what like terms do you see here? Yeah, those two add to be 2 of them. So this is not descending orders of powers, but just a way to write it. 5 over x squared plus 2 over x minus 3. Now, there's nothing special about that. It's just that's how they gave our original one, so I went back to that, putting it over there. Okay, over x plus 5 squared. Now, the only reason I did that, or the main reason I did, is now we're going to be plugging in, because why are we doing this anyway? To find the slope at that point, at x equal -1. So to me, it's just about as easy to plug in there as it would be with -1s and -2s. So that's why I went back to this form. If you like the other form better, go with it. The other form is much better to take derivatives. To me, in the denominators, it's just as easy to evaluate. So now we want m is f prime at -1. And that would be which is x is -1, so that would be okay. But -1 squared is 1, so 5 over 1 is okay. -2 -3. Okay, over okay, 16. Okay, y'all went right ahead. But what's that numerator?
Oh, 0.
0. Who cares what the denominator is? That's a big fat 0. Okay? Now, if the slope is 0, that means, plugging that in, y is equal to 0 plus b. Now, what do you think the b's got to be? What is b? mx plus b. What's b? Okay, and what you reckon the y-intercept is going to have to be? Yes, because it's a horizontal line at 1. So yeah, that's got to be 1. Y is equal to 1. There's the equation for your tangent line. Y is equal to 1. Okay? Now, since they didn't show you the problem on the PowerPoints, they sure aren't going to show you the graph. But if you look at the graph there, you'll see we got exactly that. -1, 1 is indeed. Do all of you have some type of book, either ebook or paper book? When you look at that graph there, you'll see there's a leg down here, a leg here, because you know that x can't be 0 and x can't be -5. So there's your vertical asymptote at -5, there's your vertical asymptote at 0. You're down here for that part out there, and there for the middle part, over here for the right-hand part, and there's -1, 1, and sure enough, that looks to be a horizontal slope there. Y is equal to 1. Equation for the tangent line. Remember, if they're asking for an equation, what had your answer better have in it? Okay. An equal sign. Equation. Yeah, it's got to have an equal sign. So don't give me 1. You know, that's a number. That's not an equation. Y equal 1, that's an equation. Okay. All right. See, I'm also teaching a Math down the 8, and I have to convince them of that. No, if it's asking for an equation, it's got to have an equal sign. If it's asking you to simplify, don't throw in an equal sign. There's not one there to begin with, so don't do it. Okay. So I shouldn't have done that. Okay. Now, here's example 6. We're going to have to do that one on our own because they didn't show that. I am really a little bit disappointed in this section because they're doing lots of stuff without showing the examples on the PowerPoints, but neither are they giving you some larsoncalculus.com places to go to see these done. So I was much happier with this text until I got to this section. They're just not giving you a lot of support here, it feels like. All right. So let's do this one. Original function. Y is equal to x squared plus 3x over 6. Okay? Now, how would you take the derivative of that function? Well, okay. Your derivative of your denominator is 0. So that second term, the high d low, is going to be 0. Okay? Now, over low would be put a 36 in the denominator, right? Okay? But here's the point. Since there's no variable in there, you don't need to use the quotient rule. You can rewrite this as 1 over 6 times what? X squared plus 3x. I can even do that one, I think. Now we'll take the derivative of that one. Y prime of that would be what? Okay, 1/6 of 2x plus 3. Okay? And that's a perfectly good answer. Okay? Now, if you want to distribute the 1/6 across, that would be x over 3 plus 1/2. If you wanted to. There's no reason to do that. This is a perfectly legitimate answer, but that would be what you would get if you did distribute. Okay? They wrote the y prime both ways. Well, they wrote it a different way, yet a third way. And the third way would be 2x plus 3 over 6, which probably is closer to how they wrote the numerator, which is fine. But in other words, what you can do is just ignore the 6 whatever. Don't throw it away, but put it in the denominator and take derivative of the numerator, 2x plus 3. All of this. Okay. So, let's see about this one. The B part of example 6, y is equal to 5x to the 4th over 8. What's that again? Okay, what would you do to that one before you took it? Well, I don't care. What's that?
I said, how can you just take the x off the top and put it on the side?
I can't.
I just don't understand how you can just take the x to the 4th off the top and move it to the side. Like, how can you just...
Okay. I mean, there's a couple ways you can do this. One way, if you're having trouble seeing it, you can just pull out the 5/8 as a constant, okay, times x to the 4th. That is legitimate. Do you agree with that?
Well, that's what I was asking. Like, how or why are you able to do that?
Why are you able to? Because 5x squared over 4, that would be 5 times x 4th times 1 over 8. Right? Or 5 times x over 4 over 8. Maybe that makes it easier, right? Which you could say that is 1/8 times 5 times x to the 4th, which then pull out the 5 and you have 5/8 x to the 4th. You can do it just about any way you want to, but they're all the same. Okay, they're just numbers. Those are constants. Doesn't matter if they have parts in the numerator, parts in the denominator, they're just constants. You can pull them out. How will you take the derivative once you have done that, though? 5/8 times 4x cubed. And then you notice the 4 will go into 8 twice, and that would be 5/2 x cubed. Or, lots of ways you could write it, 5x cubed over 2, if you prefer that way. Now, I'm going to, is it all right for me to clear this? Y'all need it a little longer? Okay to clear? Okay. All right, let's do the C one there. Y is equal to -3 times a 3x minus 2x squared over 7x. Okay? Anything that looks that complicated, I'd say simplify as much as you can. And what can you do to begin with? What have we been doing? Pulling out the constant. What constant do you see in that? -3/7. See that? You got 3 as a factor, or you got the minus sign, pull it out. You got the 3 as a constant times something in the numerator, and the 7 as a constant times something in the denominator. So pull out -3/7. Now what do you have left? 3x minus 2x squared. And guess what, folks? The y prime then would be oh, I'm sorry. Yes, I'm sorry. Okay, so we do have one more step. I knew we did, I just wasn't watching, okay? 3/7. What can we do with the x in the denominator? Do your high D low and low D high above it? Yeah, that would be simply 3 minus 2x. Because x goes into 3x and x goes into 2 minus 2x squared. Now, I say that, but you do have to account that originally it was down there, so I have to also say x cannot equal 0. Even though there's no problem in the world with x being 0 up here, that wasn't your original problem. X can't be 0 here, so it can't be 0 down there. Okay? So this is one of those hole in the graph type functions. X can't equal 0, even though in that form it looks like it could. In fact, that's going to be a straight line. Okay? Slope of 6/7, okay? Y-intercept of minus 9/7, okay? So it's going to be a weird straight line, but it will be a straight line. But it'll have a hole where x equals 0, because that can't be 0 here, it can't be 0 down here either. But we can still take a derivative as long as x is not equal to 0, and what would that be? -3/7, don't forget your constant, times a -2. And that would be, say again? 6/7. And I already said that, didn't I? That's the slope, okay? Now, that's the slope everywhere except where x equals 0, because there's a hole there. There's no value there, but everywhere else, it's a straight line, so it does have a constant slope, except that x equals 0. It's not that the slope's not defined there, it's there's no value there, okay, because x can't be 0. Now, I don't know if they went into all that or not. They didn't, but you do have to mentally do that. All right, let's do the D one. Y is equal to 9/5x squared. Okay? Now, would you rewrite that first? How? 9 over 5 times x to the minus 2. That's exactly how I would rewrite it. Whether they do or not, I don't know. That's how I would do it. Now you can take its derivative. Y prime would then be
9 over 5 times -2x.
times what?
Times -2x to the -3.
Okay, yeah, times negative 2x. I got it. So I would make that minus 18 over 5 x. Didn't catch all the last thing you said. 2x, you said? Ooh, I don't think so. What do we do with the exponent? Negative 3. You reduce it by 1. If that was x squared, that reduces the x. If it's x to the minus 2, it drops to x to the minus 3. And what you know here is x can't be 0 here. And of course, it still can't be 0 there either. Okay? Now, they didn't worry with that any, but they just left it that way. Now, because the original problem had x in the denominator, you could rewrite this as minus 18 over 5x cubed. If you prefer it that way, that's perfectly fine. There's nothing that says you have to. It's just that usually when the original part is given in one form, I'll usually try to write the derivative in the same basic form too. But this is a perfectly correct and good, proper answer. There's nothing wrong with it. Have we reached that time? No, it's just for, okay. Oh, I see. Okay. Great. Thanks. All right. Any questions on example 6? And guess what? They didn't do example 7 either. Okay. So let's do example 7. And we've already been doing this, but they act like it's a new concept here. But, of course, we are ahead of them, aren't we? If n is a negative integer, then there exists a positive integer k such that n is equal to negative k, right? If n is negative, you can negate it and make it k, okay? So by the quotient rule, you can write, and why would you ever want, oh, yeah, let me see. Yeah, if n is negative, and this is what we've already been doing, d by dx of x to the nth power, that's what we're taking the derivative of. But if n is negative, then move it downstairs. D by dx of, why would you do this? Why are they even messing with this? Of 1 over x to the k. Yeah. Why would you do this? I can't see why they would do it. Maybe I just slipped it into you. You still do your negative exponents the way you do a power rule, but we did that, didn't we? So they're really just redoing the power rule. And so there's no reason to ever go through this mess. If that was your problem, even if n was a negative number, the answer would be n times x to the n minus 1. Okay? Big surprise. That's what you got. Why go through all that to get what the power rule already tells you? Don't do that. Okay? Just do it. That's the form you want it. Oh, wait. I'm sorry. I wrote it wrong. No. That wasn't a minus. Yeah, I wrote it right. Yeah. Don't go through and get them in the denominators and have to move it back to the numerator and then negate and do that. Just do what it tells you to. Okay? Mystery to me why you even put that one in there. Okay? That to me is more confusing than it's worth. Okay. So let's move on to Derivatives of trigonometric functions. Like we already said, we know sines and cosines already. We've already done those. But when we get to the other four, oh boy. Knowing the derivatives of the sine and cosine functions, you can use the quotient rule to find the derivatives of the remaining trig functions. And they just pop it to you here. This one, I will show you how it works. This first one. D by dx, what is tangent x? You 3 or 4 students who know your trig so well. It's what? Oh boy. I got to go back and change that grade. No, tangent. What is the tangent? It's sine over cosine. You're making me look bad here, you know. Huh? Okay. Sine over cosine. I couldn't hear what you said. Sorry. My hearing's bad. Okay. How would you do its derivative? Okay. What's our little rule? Cosine x. Wait. Okay. Low, d high. What's the derivative of sine? No, derivative of sine is cosine. So that's cosine times cosine. That'd be cosine squared, right? Minus sine x, high, times another minus sine x, okay, over cosine squared x, okay. So here we have a cosine squared x, and minus times minus will give you a plus sine squared x over cosine squared x. And what's cosine squared x plus sine squared x? Oh, 1. Of course it is. Where are my trig students, huh? That's that one that we use a lot. That would be 1 over cosine squared x. And what's 1 over cosine squared x? Secant squared x. You got it. Secant squared x. So, derivative of tangent is secant squared. Okay? Want me to take you through all of cotangent too? Huh? You don't? Huh? Let's do it, okay? So d by dx of what is cotangent squared? Cotangent? Cosine x over sine x. Okay. And what would that be? Sine x. Wait, I was jumping ahead. Sine x, let me just write it that way to begin with, times a negative sine x, okay, minus high, which is cosine x, cosine x, okay, all over sine squared x, okay. So what do you have in the first term? Minus sine squared x minus cosine squared x over sine squared x, okay, and this would be, I really don't like negatives that much, so I want to factor it out, okay, minus, and what does that leave me with? Sine squared x plus cosine squared x over sine squared x. And that would give me, what's sine squared x plus cosine squared x? 1. So that would be a minus 1 over sine squared x, which would be, what's 1 over sine squared x? Cosecant, so that would be minus cosecant squared x. And that's exactly what they got there. Good for them. Okay? All right. Now, I don't know if this is going to get more confusing than it's worth, but you could, if you didn't remember this Pythagorean identity, which is the easy one, you could have said this is cosine over cosine, cosine squared over cosine squared would be 1 plus sine squared over cosine squared, which would be sine squared over cosine squared? Tangent squared. And 1 plus tangent squared would be secant squared. Of course you would remember that one if you couldn't remember the easy one, wouldn't you? No, I don't think so. But you could do it that way too. All right. That's the beauty of trick. In fact, the beauty of math. As long as you do the right stuff, it always, whatever way you get there, you should come out okay. Can I erase these so we can do secant? Okay or not? Okay, so let's erase. Okay. Oh, I didn't hit the right key. Okay. Yeah. All right. Let's do secant. What in the world is secant x? Root of d by dx of what is secant x? All my trig students better know this. 1 over cosine x. Notice it's not my trig student that answered the question. Huh? What is wrong here, folks? All right, what would this be? Now, this is one I wouldn't go to the minus powers, okay? That works with the power rules, but let's not do it with this one. So let's use the quotient rule here, and that would be cosine x times 0, okay? Minus yes, negative sign, so minus and a minus will make it a plus sine x, okay? All over cosine x squared, cosine squared x, right? Okay, well that's 0, okay? So what we have is a sine x over cosine squared x, right? That's kind of a big boo hiss. So what I'm going to do with that one, I'm going to rewrite this as 1 over cosine x times sine x over cosine x. That's the same thing, isn't it? I just split up my denominator and split up my numerator, right? Now what's 1 over cosine x? Say again? Well, sine over cosine is tan x. I know that's what you were answering, wasn't it? I thought so. And what's 1 over cosine x?
I always get the other ones confused.
1 over sine? 1 over cosine? Secant! Okay, finally one of my trig students remembered. Oh, I thought she said tangent. Okay. Okay, so that would be secant x times tangent x, which is exactly equal to 5. Okay? Now, this will still come out all right on that one. You want to do it? Huh? Do it. Okay. So, what is cosecant x? What is cosecant?
Cosecant is
1 over sine x, okay? And then using our quotient rule, what would this be? Sine x times 0, that goes to 0, minus cosine x. 1 times cosine x is cosine x over sine squared x. Okay, we'll do the same little trick we did before. Minus 1 over sine x times cosine x over sine x. Okay, and that would give us a minus. What's 1 over sine x? Cosecant x. And what's cosine x over sine x? Say again? Cotangent x, absolutely. And there's exactly what they get. Minus cosecant x, cotangent x. Perfect. Now, please don't forget these as fast as you forgot your trig, because next term, when we start doing integrals, you're going to need to integrate these forms, which is undoing the derivative, taking an antiderivative. So you see this will simplify to that. This will simplify to that. So we're going to be doing that. So hang on to these things. They're not erasable, okay? Just because you're through with trig doesn't mean you have to forget trig, okay? We don't want to do that, okay? All right, so there is your theorem 2.9. And we did a proof on one of them anyway, so we already did that one. Okay, and Anhil left, so that you've been the best one. Here's example 8. This one is at larsoncalculus.com, but it's also in the book, so I don't know. So, if there's your function, what's your derivative? 1 minus
secant squared x.
Secant squared x. Got it. You were reading my handwork. No, you weren't doing that. Okay. All right. So 1 minus secant squared x. The sum rule, the product rule, the addition rule, they all still work here. Okay. How about this one? That is a what? This was a difference. This is a product, so how would the product rule work? Y prime would equal to x times secant x tangent x. Excellent. Okay, you're either reading my hand or whatever. Okay, next. Plus secant x times 1. You got it. So that would just be x secant x tangent x plus secant. Let's see if they, yeah, they just, or they factored out the secant x, because that was in both terms, and then that left you an x tangent x plus 1. So you could have left 1 in there if you did it that way. So, is there, no, that's all. Then they go to example 9, but they skip example 9. So let's go back and do example 9 here. Do we have time? Oh. I have a feeling we don't have time for it. So let's pick up and go with that next time. That'll be example 9. Is where we'll begin. And homework exercises. Do any of the odds, 5 through 9, all 3 of those are at calcchat.com, 5's at calcview.com. Do any of the odds 11 through 15, they're all 3 at calcchat.com, the 11's at calcview.com. Do any of the odds 17 to 21, they're all 3 at calcchat.com, but 21's at calcview.com. Do any of the odds 23 through 27, they're all at calcchat.com, but only 23's at calcview.com. Do any of the odds 29 through 39, okay, they're only at calccheck.com. They don't have any of those at CalcView. Do any of the odds 41 to 55, they're all at CalcChat, but only 41's at CalcView. Do 57, that's the only one like that. That says using a computer algebra system. You can do it not simply, but you can do it without that if you wanted to. If you don't want to mess with it, you don't have to. Okay. Do either 59 or 61. Let me see. That may be a good place to stop. I'm not sure we're going to do any more like that. If you want to try any of the odds 63 through 67, you can. Yeah, you can do those. It's just finding equations of a tangent line, which I don't think any of the other examples are going to do that for you either. So you can still do that. And we'll pick up the rest of those next time. All right, good deal. Any questions? Good deal. Glad y'all came, the few and the faithful. I don't know where the rest of them are, but I'm glad